So today we're going to be talking about functions, and functions are a nifty little thing in math. They're not anything new in and of themselves. They're just a way of formally writing and describing the things we've gone over in math, such as graphs and equations and all that stuff there. So they're kind of a way to formalize your work so that everybody understands what you're doing. It's going to be really used in the higher levels of math. Most everything is described in terms of functions, the higher level you get in math. So it's good to kind of get the basic understanding early. That way you're used to the notation, you're used to seeing things like this, so when you get into higher level math, you can easily understand the material. Again, it's not anything new in terms of calculations. There's no big formula to remember. There's no big process to go over. It's just a way of writing and seeing and reading math, which means there's going to be a lot of vocabulary and a lot of conventions to kind of understand here, which is going to make this video a little bit longer. My apologies. But it's good to kind of get this formalization down so that you can understand it when it comes back up again. So first off, let's start with what is a function. What's the definition of a function? Well, a function, put in sort of layman's terms, is a rule for turning input values into output values. So a function is a rule that takes values, applies the rule, and spits out new values. Now we're going to start with some very basic rules here. So more often than not, people will describe it as a function machine. So this right here is the function machine. You put your number in, your rule does something, and spits out the output. So let's try a very simple rule. A very simple rule would be to simply add 2. So that's the rule of the function. I put in a number, I add 2, I spit out the value that pairs with it. So if I put in 3 to my function machine, it would add 2, and then it would spit out 5. Pretty simple, right? Let's try another one. If my rule was, let's say I put in a 4, add 2, my rule would spit out a 6. So my input would be 4, apply the rule, apply the function, and my output is 6. Now that's a very basic rule. Let's try one that's a little bit more in detail. Let's say my rule was times by 3, then add 1. So it's a 2-step rule. Times by 3, then add 1. So if I put in a 5 times 3 is 15, add 1 is 16, so my output would be 16. So the input value would be 5, apply my function rule, the output value would be 16. Again, if I try another one, let's try a basic one here. Let's try 0. If I put in 0, 0 times 3 is 0, add 1 is 1, so you get out 1. Okay. No big worries there. Now, this should remind you of something, the little process we did. This is basically an equation. If I label my input as, say, my x values and my output as my y values, then I can write this function as an equation. I can write it as x. Well, actually, let me start like this. I can write it as 3 times x plus 1 equals y. That's what my function is basically saying here. My x's are my inputs. I times them by 3, then I add 1, and I get my outputs, which are y. So again, if I plug in a 2 for x, I would do, my function rule would be 3 times 2 plus 1 equals, 3 times 2 is 6 plus 1 is 7. So my output would be 7. And that's generally how we deal with functions. We say our input values are the x's, our output values are the y's, and the actual function machine, the actual function rule of the process is the equation that you're given. So more often than not, functions will be put in the form of an equation. That way we don't have to keep drawing this little function machine picture here, as cool as it might seem. Okay? We don't want to have to draw this little diagram here every time we do a function, so we just write it as an equation. Again, as I said, these function stuffs are not anything new. They're just a way of thinking and seeing and writing the stuff you've already done, like equations. So the input of a function is the x, the output of a function is y, and the function itself is the entire equation, how the numbers interact. It's a relationship between x values and y values. That's what the formal definition of a function is. It's the relationship between an x value and a y value. Okay? You give it the x value, it does its rule, it gets out the y pair. Now, there is only one rule in order to make an equation a function, because not all equations are functions. There's one rule that makes it a function, and that is the rule that you can only have one output for any given input. So if you put one number into the function, you get out one number. You don't get out two numbers. For example, let's do one that's not a function. Let me clear this here. Let's say, I'm not going to write a rule, but let's say I plugged in 4 and my function did the rule and it spit out 10 and 2. I put in a 4 and it spit out both 10 and 2. That would not be a function because I put in one number and whatever my rule did, it spit out two numbers, which can't happen. It should only spit out one number for one number. I put one number in, I get one number out. That's what a function does. So if your equation does not follow that rule, then your equation is not a function. A function is one in, one out. So if I plugged in 4 and I got out just 10, then that would be a function because I put one in and I got one out. But if I get out 2 or more numbers for just one input, that's no good. So what are some equations that look like functions and some that don't? Well, let's try the ones down here. Y equals 2x squared. Well, okay, that's a function. If I put a number in for x, I'm only going to get out one number for y. If I put 1 in for x, it'd be y equals 2 times 1 squared. Some quick math here. 1 squared is 1. 1 times 2 is 2. So y equals 2. So my input is 1. My output is 2. I get a 1-to-1 rule, so that's good. I put one number in, I got one number out. Same thing if I put in a 3. Y equals 2 times 3 squared. 3 squared is 9. 9 times 2 is 18. And that would be my output value. So I put one number in, and I got one number out. So this right here is a nice function. You put a number in, you get a number out. Non-functions are actually a little bit harder to put in because they're not that common, at least not at the level we're working at. But one non-function would be this. It looks a little weird, so let's see how this works. You put in an x, and then your outputs are whatever numbers that, when squared, gets you x, which sounds a little bit weird. So let me show you an example. Let's say I put in a 4. Okay. So this is asking me, if I put a 4 in for x, what numbers, when squared, get me 4? So if I go through the numbers here, 1 squared is 1. That's not 4, so 1 can't work. 2 squared is 4, so 2 would be okay. So 2 works. So that's 2 squared. So that's my y there. That's my output. That's my y. But there's also another number that works in here as well. If I put in a 4, I could also get out a -2. Because -2 squared is also 4. So it's also a y. So this machine here, whatever this machine is, let me go back up here to my little function machine. This machine here, if I put in a 4, I can get out 2, or I can get out -2. Because both of those, when squared, get me 4. So this right here is not a function. This does not give me a 1-to-1 give. I put in one number, and now I've gotten out two numbers. That can't work. It works the same with all the other numbers, too. If I plug in a 9, for x, that means my two possible outcomes are 3 or -3. If I put a 9, 3 squared is 9, and -3 squared is 9. So again, it's not a function because every time I put in an input, I get out two outputs. And that can't work. As we know, as we just said, a function has to be 1-to-1. One input gives you one output. Again, they're kind of hard to write because, again, they're not that common, and they don't work well as equations because they have that dual aspect to them. But functions are pretty general, easy to see, and those are the things you're going to be working with for the most part. Now, as I said before, functions don't have to be just represented by equations. That's the most common way to represent them. But they can also be represented by graphs and by tables. So let's see how we can tell a function from a graph. Now again, it's an equation. We could tell if something's a function by doing this little check here to see if it's a 1-to-1. Or I shouldn't say 1-to-1. To see if we put in one input, we get out one output. For a graph, it's kind of hard to tell that because you're not given an equation, you're just given a picture. So for a graph, there's actually a special test to see if it's a function. It's called the vertical line test. And what that does is if you draw a vertical line straight down all the way through your graph, if that vertical line does not touch the graph, does not touch the picture, does not touch the design, if that vertical line does not touch the design more than one time in any one spot, then it is a function. If the vertical line crosses the graph at more than one point at any one spot, then it is not a function. So what do I mean by that? Well, let's take a look at these two pictures here. This picture is a function because if I draw my vertical lines, let me actually get a line here so I don't have to draw these by hand because that would be bad. If I draw a vertical line through the entire graph, try to make these as straight as I can, they will not hit the graph more than once at any one time. So I hit it once here, I hit it once here, I hit it once here. Each vertical line is hitting the graph only once. Only once. And you can do that as many times as you want. You will never get one vertical line to hit this graph more than one time. So this is a function because it passes the vertical line test. This, however, is not, because what happens is if I draw a vertical line here, this vertical line hits the graph twice. Once up here and once down here. So does this vertical line, and so does this vertical line, and so does this vertical line. So there's a lot of times where this graph fails the vertical line test because it hits the graph more than once. And there's more than one design for this. So for example, it only needs to happen once. If this instance, if this double hit here happens just one time, then it's not a function. So let me show you an example about one that would be close but not quite. If I drew this design here, let's say I have this here, I double back like this. Let's say that was my graph. This would fail the vertical line test because it hits it more than one time right here. And kind of in this little zone right here, it hits it more than once. Even though it's okay over here, and it's okay over here, it's not okay over here, therefore the entire thing is not a function. So the vertical line test has to be passed throughout the entire graph, not just a few points. So again, vertical line test, just draw vertical lines straight down or use your pencil and kind of slide it along the graph if you want and see if your pencil hits the graph at more than one spot. Use your pencil as that vertical line and see if it hits it at more than one spot. If it does, it's not a function. If it doesn't, if it hits it in just one spot each time, then it is a function. Another less common way is that functions will never double back on themselves. So you see this graph keeps going left to right. It doesn't double back. This graph doubles back. This graph goes right, 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 and then it turns back and now it's going left, and then it turns back and now it's going right, right, right. So it doubles back on itself. This double backing action causes it to be not a function. This graph does it too. This graph is going, if we start here, it's going left, 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 turn, now it's going backwards. So this graph doubles back on itself as well, therefore it's also not a function. So you can do the vertical line test or you can do the double back test. Either one works. And then lastly, graphs can be looked at as functions rather. Functions can be looked at as tables. And tables are really easy to see if it's a function or not because all you're doing is seeing if there's a repeated x value. Because remember, a function cannot have an x value give more than one output. Remember, x's are your inputs, y's are your outputs. So if my input occurs twice with two different outputs, then that means it's not a function. So for example, in this case, I have 1, 0, -2, -1. Each input happens only once, so I'm good. This is a function. Each x happens only once. Here I have 2, 3, 0, and 2. Well, here I have a problem because this 2 and this 2 happen twice, and they're both x values. So I have an x value that's repeated, and it's giving me two different inputs. I put in a 2, I get out a 5, and I also get out a 1. That's what this one tells me. I put in a 2, I get out a 5. I put in a 2, and I also get out a 1. That can't happen in a function, so this is a non-function because the 2's repeat. So for a table, if you want to check if it's a function, just see if your x's repeat. If they do, it's not a function. If they don't, it is a function. Now remember, we really don't care about the y's. The y's can repeat or all be different or all be the same number. We don't care. It's all about the x's. Do your inputs repeat? Don't care about your y's. So to wrap up this first one here, the main idea, again, is that a function gives you one output for one input, and we call the inputs x, and we call the outputs y, and usually our functions will be an equation. Again, a lot of information about conventions and whatnot, so don't be afraid to kind of pause and, digest this a little bit before going on if you need. So since we're writing stuff as functions, we can identify two different pieces of information about them now, which apply to functions. The first is the domain, and the second is the range. So the domain of a function is what we call all the possible inputs we can put in, all the possible numbers we can put in as inputs to the function. So if I scroll back here a little bit, it's all the numbers I can put right here. Every possible number I can plug into the function is the domain. The range is every possible number I can get out of the function. So the range is the set of all possible outputs. So the range is a collection of every possible number my function can spit out. The domain is a set of all the possible numbers I can put into my function. Now I might be saying, well, can I put any number into any function? No, not quite. And we'll see some of those coming up here. So how do we write the domain and range? We can't just write it out in words, or we could write it out in words, but that's going to take too long. So we write it out one of two ways. The first way is called set notation, which is this way right here. So let's say my function is only accepting the numbers 1, 2, and 3. Those are the only numbers that my function will accept. Well, the way I write my domain is I'd say the domain of my function is equal to the set of 1, 2, and 3. And I use little curly brackets to denote set notation. So that'd be how I write my domain. And again, I apologize for my sloppy writing here. I am using a slightly different setup here to make this video, so my writing is going to be a little bit more off than normal. So this is one way to write a domain and a range. It works for a range as well. You just replace the D with an R. You can also write it as an inequality. So if your domain is like between 5 and 10, let's say my function will accept all the numbers between 5 and 10. I can say that my domain is equal to 5 less than x less than 10. So this says my function will accept all the numbers between 5 and 10, not including 5 and 10. If I want to include 5 and 10, if my function will also accept the numbers 5 and 10 themselves, then I'd have to put the little or equal to symbol there to show that 5 and 10 themselves work as well. So inequalities are very picky in this case, so be careful. Now, graphs are a big thing with functions. This domain and range stuff is very apparent on a graph. And that's usually what the questions will be on a math test or something, is you're given a graph and you're asked to describe the domain and the range. You can think about the domain and range as kind of the walls or the borders of a graph. It's kind of the boxing in of your graph. So the domain is how far left and right the graph can go, and the range is how far up and down the graph can go. So let's take a look at this first graph here. I'll put a D here for domain and an R here for range. So I'm looking at this graph here. This graph has a start and an end. It does not go on forever. So it's not a line, but it just has a start and an end spot. My domain is the furthest left x value. Remember, domain is the x's and the range is the y's. So how far left can my graph go in terms of x numbers? Well, I can go left, left, left. My graph seems to stop right here. I don't go past this point. So that is the point x is -7. And it's a dot there, so it includes that -7. So I'd have -7 less than or equal to x, because it does include the -7. There's a solid dot there, which means that graph hits the -7 for the x value. And then how far right does the graph go? Well, I go from here, I go right, 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 right. I stop here. So my graph goes all the way up to, it seems, this right here is the x equals 5 point. So it stops at x equaling 5. So my graph bounces between -7 and +5 in terms of left and right. So those are kind of like the walls of my graph. If I put up a wall here, so my graph starts at this wall. Ooh, that's kind of an ugly wall there. Let me try to redo that. My graph starts at this wall and it stops at this wall. So that's the wall, that's the left and right walls of my graph. Now I need to figure out the floor and the ceiling, the bottom and the top. That's my range. So let's start with the bottom. My graph seems to go all the way down to right here is -2. So my graph goes all the way down to -2. So I'm going to go -2 less than or equal to y, because remember, the y's are my range. And again, there's a solid dot there, so it does include that -2. And I go all the way up, 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 until I get right here, which looks to be at the 8 spot. So my graph goes all the way up, my y's go all the way up to 8. So again, what this says is that my graph bounces between the numbers -2 and 8 for the y values. Again, they kind of act like a wall. So let me put my walls again. So we have a wall here, and we have a wall here. So as I said, the domain and range kind of frame your graph. They're kind of the boundary points of your graph. So this domain says my graph goes from -7 to +5. And the range says my graph goes all the way down to -2 and all the way up to +8. So these are all the possible numbers I can put in. These are all the possible numbers I can get out. And usually you're going to be writing them as an inequality, except for some special cases we'll go over. Let's try a few more just to make sure we're clear. So for this one here, I'm going to write my domain, write my range. We'll do the domain first. So I go all the way left right here. It looks to be about -7. Less than or equal to. And I go all the way over here. Looks to be +5. So x less than or equal to 5. And again, we do write it as this sort of combined inequality here. So our x is in the middle, our lower bound is to the left, our upper bound is to the right. That's how we write our domain and range. Lower bound to the left, upper bound to the right, x in the middle. My range goes all the way down to -4. So I go all the way down to -4, y, and then I go up, 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 up. It looks like I hit +9. Yeah, it looks like +9. So all the way up to 9. And that's my domain and range. Again, no big long formula. It's just a matter of analysis. Now, you might be noticing I'm using these less than or equal to signs a lot. If this dot here was an open circle, so let's say, look, I'm going to kind of draw a quick version of it. Let's say it looked like this. I had an open circle here. Then my graph went all the way down, then all the way up. So if I have an open circle on the graph, what that means is that my graph gets close to that point, but it doesn't actually touch that point. So if that was an open circle, I would just use this symbol instead. I wouldn't use the less than or equal to because my graph doesn't actually hit the -7. It just gets really, really, really close. But because it's a closed circle, that's when I use the or equal. That's why I use the line under it, because there's a closed circle there. Last one on this page here. Again, domain and range. Once you get the hang of it, it's not too hard. You're just looking for the left, the right, the up, and the down. But you do have to make sure you're careful about it because they can get a little tricky if they have a lot of curves. So all the way over here looks to be very, very close to -9. So we'll go ahead and do -9. I think I might have misplaced that dot slightly to the right, but it's close enough to -9. We'll call it -9. X. Then my rightmost bound. So over, 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 over. We hit a pretty clear 8 here. So that'd be 8. My range, we'll start on the bottom. That's pretty clear. It's a -7. So -7 right there. Oops, my bad. -9, it looks like, because -9 comes after 8, not -7. So yeah, it's a -9 there. Almost made a mistake here. That'd be bad because I had to redo the whole video. And we go all the way up, 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 up. Right here is a 4. So we go all the way up till we get to +4. And that's my domain and range. Okay. So again, they're just leftmost bound, rightmost bound, lower bound, upper bound. Left and right domain, up and down your y, your range. Okay. Now there are some tricky graphs that are a little different. So let's take a look at some of those. The first one is this graph. So if you see here, let's do my domain and range real quick. Domain, range, equals, equals. So if you see here, this graph doesn't have an endpoint. it goes on. That's what these arrows mean. It goes on forever this way, and it goes on forever this way. So there is no left and right boundary. There is no left and right wall. It goes on forever. So the way I write that, I can write it in one of two ways. If it goes on forever in both directions, what I can do is I can say the domain is all real numbers. That's what this little R symbol means here, is all real numbers. So it means every possible number that I'm working with here can work. And we say all reals because there are a set of numbers called imaginary numbers or complex numbers. I won't get into detail about that, but the reason I say real numbers is to define that we're not including those kind of special high-end numbers there. So if I can work with every single number on the graph, then it's all real numbers. If there's no left and right walls, if it goes on forever, it's all real numbers. Or you could also write it like this if you want. You could say the graph goes from negative infinity less than x less than positive infinity. So again, you use the infinity symbol to show that your graph is going on forever in both directions. Notice here I'm using the ones without the lines on them because you can't actually reach infinity. So you don't put the less than or equal to's, you just put the less thans. Okay? But it says you go on forever to the left and you go on forever to the right. So the infinity symbols are used to go forever left or forever right or both in this case. Same for my range. My graph is going to keep going up and it's going to keep going down in this direction. So my range is again all real numbers. Or I could use the inequality down here and just swap out the x for a y. Okay? So lines are actually pretty easy because the domain and range are just usually these. Now sometimes your graph will just be a set of dots. Like here, there's no connection. I'm only including these 4 specific numbers. So in this case, this is when we use the set notation form. Because an inequality doesn't make sense here. I'm not describing a range of values. I'm describing 4 key points. So I'm just simply going to state for my domain all of the x numbers that work. So let's see what these points are. This point here is -7, +2, right? So I'll label it here. -7, comma 2. That's a 7 there. -7. This point right here looks to be -4, +6. So -4, +6. This point right here is 0, 3. 0, 3. And this point right here is 5, 6. So 5, 6. So my domain is all the possible numbers I can put into the function, all the possible inputs, all the possible x's. Well, my x's are -7, -4, 0, and 5. So I'm just going to write them down. -7, -4, 0, and 5. Again, I wouldn't use inequalities here. I would just use the set notation we talked about. The range would be the same, except I'm going to write down all the y values that I have. So I have 2, 6, 3, and 6. So I'm going to write down 2, 3, and 6. I don't have to write down 6 twice. You don't have to write down the numbers twice if you don't want to. If you do, again, it's unconventional, but you can if you'd like. And notice here I put them in order. You don't have to put them in order. It's just a nice thing to do because numbers in order are easier to work with. But if your graph is just a set of dots, then your domain and range are going to be just single sets of points. So you're just going to write down all the possible points for the x's and all the possible points for the y's for that set of dots, whether it be 5 dots, 10 dots, or 11 dots. If they're not connected in a line like these were, if they're not connected like these, then you just write down the numbers as a set. If they are connected and you include all the points between them, then you write down the inequality, because this inequality means that we're going from this point and we're hitting all the points along the way. So this means we're hitting every single point between the dots as well as the dots themselves. This notation means we're just hitting the dots, not anything in between. And one graph I didn't put on here that I'm going to try to show real quick is if we have a graph that's kind of a combination of the two. Again, I'm going to draw the best I can here because actually, you know what? Why don't I use my little line tool, which will make these lines a little straighter, hopefully give us a little bit better. So let's say I have a graph that looked like this. Okay, let's say I have a dot over here. That's where my graph starts, and it does this sort of thing and goes on forever. Okay. Now let's say this point right here is 2, comma 5, or sorry, I should say -2, comma 5. And we'll say this point down here, this is the lowest point. We'll say the lowest point is at -1, comma -4. Okay. So the way I write my domain and range here is, if you notice, my domain does have a start. My domain starts at -2. That's the leftmost point. That's the lowest x value I can use. But it doesn't have a highest x value because there's an arrow here. So it keeps going on forever in that direction. So I'd say -2 less than x, less than or equal to x, because we do include it, less than infinity. Because I keep going on forever and ever and ever in that direction. So I don't have a bound on the right side, but I do have a boundary on the left side, that -2 there. That's my wall for the left side, whereas I have no wall for the right side. Same for the range. My range, it has a lowest point right here. And remember, my range is my y's. So it has a lowest point of -4. My range goes all the way down to -4, less than or equal to y. But my range doesn't have an upper bound, so it'd be less than infinity. And if this graph was flipped, so if this arrow was on this side and these points were on this side, so if the arrow was over on the left and the points were over on the right, this domain and range would look pretty similar, except that I'd have a negative infinity over here because I don't have a leftmost bound now. If my arrow was going this way, if my arrow was pointing in this direction, if this graph was flipped left to right, my leftmost bound wouldn't exist. So I'd put a negative infinity over here, and I'd have a starting point over here with the +2 or whatever would be over here. So you can have a mixture of both. You can put in these infinities when they're appropriate. Again, a quick rule of thumb is if your graph goes on forever to the right, then you have positive infinity on the right of your inequality. If your graph goes on forever to the left, then you have a negative infinity to the left of your inequality. If your graph goes forever up, you have a positive infinity on the right of your range. If your graph goes forever down, you have a negative infinity on the left of your range. Okay? So these aren't too common, but they do pop up every now and then. So one thing about these domain ranges, if we take the last two we did, is that sometimes they're what are called continuous and sometimes they're what are called discrete. So continuous means there's a line connecting the dots of the graph. It means that the domain and range does not skip any numbers inside the boundary. Discrete means that on a graph, it's just a series of dots. The domain and range doesn't contain the in-between points, it's just a series of specific values that we're using. So you have a countable number of points you can do. So again, on a graph here, look at this. Let me give myself some space. This is a continuous domain because I have all the points in between my values. My graph is a nice straight, not straight, I shouldn't say, but a nice cohesive line. There are no breaks in it. It does not stop and start. It's a nice continuous graph. So my domain would be from here, which is -7, less than or equal to x, which is less than or equal to +8. Again, my range is the same way. If you want to think of that for yourself right now, you can go ahead and pause it real quick. But my range is going to be from -3, and then I go all the way up to my highest point, which looks to be about 6. So a nice continuous graph. Discrete, however, means that my graph is just kind of a series of points, a series of dots. So notice there's no line connecting these. So my domain is just the x value of each of these dots, and my range is the y value of each of these dots. So my domain would be, I'm going to use my set notation here. We have -7. This one looks to be about -5. This one is +2. And this one is +8. That's my domain. And then my range is, looks to be my lowest point here is -3. Then my next lowest point is 1. My next lowest point is 2. And then my highest point is 6. So that's how I'd write my domain and range for a series of dots versus how I'd write them for a continuous graph. Okay? So a continuous graph is usually described as one you can draw without ever having to pick up your pencil. I can draw this line without ever having to pick up my pencil. I can't do that here. I have to draw a dot, pick up my pencil, draw a dot, pick up my pencil, draw a dot, pick up my pencil, draw a dot. So this is a discrete domain. This is a continuous domain. Now, there are something called discontinuous domains, which are not really discrete, but they're not really continuous, and that's for another day there. But for right now, just continuous, nice flowing line, discrete series of points. Okay? Discrete is set notation for domain and range. Continuous is inequality notation for domain and range. Now, in a word problem when you don't have a graph, this is kind of harder to tell. But there's a really easy trick to know whether it's discrete or continuous in a word problem. If the domain is something you measure, then it's continuous. If the domain is something you count, then it's discrete. What do we mean by measure and count? If you would have to take out a ruler or some sort of tool to measure the numbers you're putting in, then it's a continuous domain because you can include the decimal values. You can be 8.5 feet tall, or you can have 1.23 seconds. But if you have to count them, like let's say you're counting the numbers of cars in a parking lot, you can't count half a car or 1.23 car. You have to count them as 1 car, 2 cars, 3 cars, 4 cars. So that'd be a discrete counting. 1 car, 2 cars, 3 cars, 4 cars. Whereas continuous would be something like you're measuring the speed of a person or the speed of a car. Because you can go 3.5 miles per second or 65.647 miles per hour. So continuous is something you measure that can include decimals and fractions. Discrete is something you count. So let's see some examples here. A chemist uses a function that takes the altitude of a chemical and gives the boiling point temperature of the chemical for that altitude. Is the domain, should be a period here, is the domain discrete or continuous? So let's see what the function's inputs and outputs are. The input is the altitude that the chemical is at. So the input is the altitude. Again, I'm going to try to spell this the best I can with my sloppy handwriting here. Altitude. That's what I give the function the chemist is using. I give it the altitude. So the chemist takes the altitude, puts it in the function, and the output is the boiling point. I'll say boiling temp, just to make it easier on my writing here. Now notice here, it's just asking what is the domain, continuous or discrete. We normally don't talk about the range being continuous or discrete because the range depends on the domain. Because remember, the function works by you giving it an input and spitting out an output. So if your domain is continuous, then your range is going to be continuous. If your domain is discrete, then your range is probably going to be discrete. So that's why we only talk about the domain and range, or sorry, that's why we only talk about the domain being continuous or discrete, because that's really the only one we're worried about, because that will imply what the range is. So, altitude. Altitude is measured in feet. It's the feet above sea level that you're at. Altitude is something we measure. We don't count the altitude, we measure it. Therefore, this domain is going to be continuous because we have to measure how far above sea level the chemical is at. So we don't count 1 feet, 2 feet, 3 feet, 4 feet. We have to measure with a ruler or with some sort of tool to measure how far up the chemical is or how far down the chemical is if it's below sea level for our input. So we can be 2.5 feet, or we can be 207.65 feet above sea level, or we can be negative 5.43 feet below sea level. We can be all these decimals and fraction numbers because we're measuring the feet. Therefore, it's a continuous domain because we're measuring it in terms of feet. So if your domain can be negative numbers, that's an automatic continuous most of the time. There are some special cases, but most of the time, if your domain can be negative, then it's continuous. And our altitude can be negative. Now, you can have continuous domains that aren't negative. But if it can be negative, that's usually an automatic continuous. Let's look at one that might not be continuous. So an insurance company takes the number of times somebody has been in an accident, so that's their input. The number of times somebody's been in an accident, that's the input value, and uses that to calculate the cost of their insurance. So that's the output value, the cost of their insurance. So they put in the number of times they've been in an accident. The function gives them the cost that they should charge for insurance. Well, in this case, we don't measure how many times somebody's been in an accident. We count. We say you've been in an accident 1 time, or 2 times, or 3 times. There's no such thing as a half accident or a 0.53 accident. It's just 1, 2, 3, 4, and so on. So this domain is discrete because I count the number of accidents. I don't measure the number of accidents, I count them. Okay. So the input here, being the number of times somebody's been in an accident, is a discrete input, a discrete domain, because you count those. This one here is a little bit hard to see. It says a car is traveling at a rate of 65 miles per hour. The driver hits the brakes, and the function, and it gives us the equation here, gives the speed of the car, that's the s, speed of the car, after t seconds, that's the input, since the brakes were used. So t is my input, s is my output. I put in how many seconds after it's been since I hit the brakes, and I get out the speed my car is currently going. Because again, if you're driving down the road and you suddenly hit the brakes, your car doesn't go to an automatic stop. It glides for a bit. So your speed is going down, but it's still going to be going a little bit after you've hit the brakes. So this function will tell you, if you plug in the amount of time in seconds after you've hit the brakes, it will tell you how fast you were going at that time. Our question is this discrete or continuous? Well, because it's time, because it's something we can measure, it's going to be a continuous domain. Because we can put in half a second, or 1.23 seconds, or 5.6 seconds. So our time, while it can't be negative, our time can be these decimals and fractional numbers. Therefore, it is a continuous domain because it can include these oddball numbers. We don't count the seconds. We measure the seconds using a stopwatch or some sort of measuring device. So you can put in decimals, you can put in fractions, you can put in whole numbers, therefore it's continuous. Time is almost always going to be a continuous domain. And remember, in a function, the variable that's by itself, that's your output. The variable that's with all the other numbers doing stuff with them, that's your input. So I input time, and I get out the speed. That's how this function machine works for this problem. Now, linear equations are a little special because they have really easy domains and ranges. The domain and range of any linear equation, for the most part, is going to be all real numbers. As I told you before, you can write it like this. So for almost any linear equation, your domain and range is just going to be all real numbers, because if you look at a line goes on forever in both directions. It's going to go, it's going to go on forever up, it's going to go on forever down, it's going to go on forever right, it's going to go on forever left. So a line, even the lines that go the other way. So this line is squiggly, but it's also going to go on forever left, forever right, forever up, and forever down. So linear equations will almost always have this domain, because I can plug in any number I want for x and get out any number I want for y. So every single possible number you can think of, you can plug in for x, and every single possible number you can think of, you can get out for y. So these domains are almost always going to be all reals, and these ranges are almost always going to be all reals. There's no number I can put in here that would break the equation. There's no number I can put in for x that would suddenly make me say, oh, I can't do this anymore. It's just take the number, double it, and add 5. Nice little linear equation. The only time this is not true is when it's put into a context, like a word problem. So let's take a look at this one. We have a taxi company charging 50 cents per mile and a $5 flat rate. We want to express the cost for X miles. So this means that I want to put in the number of miles and get out the cost. So my output is the cost, that's my y. My input is the miles, that's my x. So I would say the cost of the cab, y, is equal to 50 cents per mile, so 0.50 times x, plus the $5 flat rate. That's my linear equation. 50 cents a mile, $5 flat rate. Now, normally, if I just wrote this down by itself, I would say the domain and range are all real numbers. It's a linear equation. If you graph this, you'll get a line. I can plug in any number I want for x, and it's okay. But because we have a context to this x and this y mean something. This x is the number of miles the cab drives, and this y is the amount you pay to the cab driver. So you actually can't put everything you want in it for x, because what number can't you use for x? Well, if x is the number of miles it drives, x cannot be any negative number. You cannot put in a negative number for x because you cannot drive negative miles. You cannot tell a cab driver, I want to go -1 miles. Similarly, you cannot pay the cab driver anything less than $5. So I'll put less than $5. Why can't you pay him anything less than $5? Well, because there's a $5 flat rate. If you go 0 miles, you still pay him $5 for just getting in the cab. That's how flat rate works. That's why companies do them. That way, if you go there and you take a cab for just like half a foot, you just didn't waste their time. They at least get $5 out of you. So I cannot pay the cab driver anything less than 5. Let me get rid of that dash mark there because that's going to annoy me. I cannot pay the cab driver anything less than $5, and I cannot go negative number of miles. So my domain and range actually do have bounds here because it's a word problem. So my domain and range would be as follows. My domain would be all the x's that are bigger than or equal to 0. I cannot do any negative numbers. I can do from 0 on up. Theoretically, I could go 0 miles. I still have to pay him $5, but I could do that. So I can go anything from 0 on up. I just can't go below 0. Now, if you want to, you could put this as well. The little infinity stuff we were talking about, you can do that. Or you can just leave it as x bigger than or equal to 0. That's fine too. For the range, I cannot pay the cabbie anything less than $5. So my range, all the possible costs here, is 5 on up. The amount I pay the cabbie is going to be $5 or more, depending on how far I go. And again, if you want to put the little infinity at the end, you can. So the context are what give the linear equations their trickiness, because it goes from being a very simple domain and range to being a very picky one. So you have to make sure you read the problem carefully and figure out what numbers can I use and what numbers can't I use. And the last thing here, whoops, sorry, my bad. There we go. The last thing here is on function notation. So function notation is a way of writing equations so it's clear about what the function is telling you. Now, it sounds a little bit weird, but let me show you here. We'll take the same exact word problem. We have the equation y equals 0.50x plus 5. So that was the equation for how much it would cost us to go that many miles. In a function notation, it would look something like this. It would say f of x is equal to 0.50 x plus 5. That's all it would do. It would go from being y to being this thing. This right here is described as f of x. It is not f times x. It is not a multiplication. The f here stands for function. And actually, in truth, it's just simply the name of the function. This is what we would call function f. I could replace this f with a g. I could have written g of x equals 0.50 x plus 5. Put a little bit bigger dot there. So this is the same thing. This would be function g. So this little front number here, or the letter here, is not really a variable so much as it is a name. This is the name of the function. Function f, function g, function x, function k. We could even say function Fred if we want to. I could put Fred of x. Okay? So this little thing right here is just why it's called function notation, because it tells you the name of the function. And the reason we do this is because, let's say I had a bunch of different cab companies that I was analyzing the costs for. I wouldn't have to write down a bunch of y's here. Well, let's say another cab company is 45 cents a mile and a $2 flat rate. I'd write down y equals 45 cents a mile and a $2 flat rate. So let's say this was another cab company. Charges 45 cents a mile and a $2 flat rate. If I was analyzing these two companies, it'd be kind of hard to tell them apart when I get down to the nitty-gritty because they're both in terms of y. Whereas if this was f of x and this here was g of x, then it'd be easier to keep them separate because I could say function f does this, function g does that. I could call them function f and function g rather than cab company 1, cab company 2. I'd say function f, function g, that's how I identify them. So this beginning part is the name of the function. This middle part right here is what your domain is. In this case, my domain is x. If I want to be really formal, I could do it like this. I could say f of m is equal to 0.50m plus 5. This middle number in here, this number in parentheses, has to be the same variable that you're using on the other side, because this tells you what your input is. In this case, it's telling me my input is m, which is probably going to be the miles I go. So it's telling me that I put in the miles and I get out my output. Or if you want to be really, really, really detailed, what you could do is do this like this. You could say, I'm going to try to use my best handwriting here. You could say C of m. Let me try that again. One more time here. C of m is equal to 0.50m plus 5. And I'm going to make that m a little bit nicer here. Again, I apologize. Like I said, I am using a new setup here, which is throwing off my handwriting more than normal. So, my apologies. So this right here would be a very formal way of writing, because this tells me that C is my output, that's my cost, and my cost is determined by my m, which is the number of miles I go. And when you get to higher level math, this is how they would write it. They'd make the function name something that means a relationship that you're using, and they make the input name be something that makes a relationship to what you're using. So in this case, C for cost, M for miles. That way, just at a very quick glance, people know what you're talking about. The cost is determined by the miles, and this is how you get it. So this is kind of like a tier 1. This is kind of like the beginning of function notation. This is kind of like the middle ground of function notation, and this is kind of the very end of function notation. This is the most formal you can get, and probably the best way to write your stuff. But a function notation at its core is simply replacing y with f of something or g of something. That way you can give the function a name rather than just having everything be called out as y. So for all intents and purposes, y and f of x or y and g of x or any of that is the exact same thing. Okay? It's just one is in function notation, one is what you would call xy notation. Okay? So this right here is XY notation, good for graphing. These right here are function notation. Okay? It's just a very simple swap from Y to this that makes it function notation. Okay? Or from Y to this, which makes it function notation. But it's a way of describing what the heck is happening at a very quick glance. What are the things you're using? I'm using the cost, which is why C is here, and the cost is being determined by how many miles I go. Not the other way around. The cost is influenced by my miles, not the other way around. That's why functional notation is good, because it gives you, again, a very quick idea about what's happening at a very quick glance. So like I said, notation has a lot of conventions, a lot of kind of rethinking of things, no big calculations, no big procedures, just a lot of ways to kind of retrain your brain to how to see this stuff more formally. Like I said, this really picks up in higher level math. Algebra 1 and Algebra 2 kind of get into it a lot, but college level math, almost everything is in terms of functions, and even a little bit of later Algebra 2, geometry, trig, and calc, more so trig and calc. A lot of stuff is related in this kind of notation here. Because when you get to those courses, you'll see that function notation makes things a lot easier to understand rather than just doing X and Y for every single thing. Because it can get very confusing using X and Y for every single thing. That's why we like to give things names so we can differentiate them when we're looking with more than one situation at a time. So, like I said, kind of a long video. Pause it to digest a little bit. If you want to go back and review certain parts, you're more than welcome to. Obviously, I'm not going to stop you. But again, hope you enjoyed the video. Have a good day.